Good afternoon. Happy Friday to everybody. Welcome to lecture. I'm going to start off with a molecule of the day today. Today's molecule of the day is vitamin D3. This is an important nutritional compound that you need to have in your diet or get from or have it synthesized in your body in order to have healthy bones. This is the structure of the molecule. It derives from cholesterol. So cholesterol is a natural lipid that's present in your body. When that gets exposed to UV light, that promotes a reaction that causes cholesterol, a ring in cholesterol, to break. And that generates this molecule. And what's interesting about this molecule, besides its nutritional importance, is that it's got a conjugated system. So there is a double bond here, and a double bond here, and they're all adjacent to one another such that their p orbitals can overlap. So this is a conjugated system. And you can lasso out regions of conjugation if you want, and so this is one of the things that you're probably going to need to do in the homework, and I definitely ask questions like this on the exam, is like lasso out the carbon atoms that are conjugated, or the atoms that are conjugated. It'll be carbons, it might be a nitrogen or an oxygen or a sulfur if it's next to a double bond. Remember last time we learned that XYZ rule that helped us understand that if you have a double bond between two atoms, X and Y, and then next to it, there's a Z element that has a lone pair. The Z atom is sp2 hybridized and the lone pair is in a p orbital. So that was a big lesson from last time. Cholesterol is an important one. It's also kind of good to talk about this one because of basically the changing of the seasons. So we're going from this like heavy, intense sunlight season to a much sort of darker, dimmer sun type season. And so people can get vitamin D from exposure to the sun, and that's helpful. But in the darker times of the year, that there's less of that available. And so, supplements of vitamin D or vitamin D fortified foods are oftentimes used to help mitigate those sorts of problems, especially for people who live in northern climates like us, where we don't get all that much sun, and we got to cover up a lot of the time. So basically you need to cover up to prevent sunburn because that's bad, but you need some amount of sunlight to get this molecule, and so there's a balance basically. All right, molecule of the day. Any questions about molecule of the day? All right, then let's talk about our survey question. The survey question is about a polymer. So this polymer is called polymethyl methacrylate. I'm going to put that name down here. Polymethyl methacrylate. It has an abbreviation. It goes by PMM. It's a real common polymer. It gets used in a lot of different plastics type applications. Most people are going to be familiar with it from acrylic, which is a generic name for the plastic that you're seeing here. Brand names for this would be plexiglass. If you've ever seen like plexiglass advertised, it's a substitute for glass. It's kind of like safety glass. It's a transparent like glass, but it's not, doesn't shatter like glass does. Another brand name for it is lucite. So if you've seen those polymers, that's what this is. So the question in the survey is asking what monomer would this polymer come from? If you were to pick a monomer to polymerize to generate this polymer, what would it be? So what you got here is a bunch of repeating units. What you need to do is to find the smallest repeating unit that could come from an alkene. So when you're looking at this molecule, look for the pattern. What pattern repeats? CH2 and then carbon with methyl and ester. CH2, carbon with methyl and ester. CH2, carbon with methyl and ester, and it goes on and on and on like that. So the smallest repeating bit is this part right here, and I'm just going to lasso out the one in the middle. But really, each one of these represents, I'll do the other ones as well. This represents another monomer, so each one of these circled regions that I'm highlighting comes from a monomer unit, and it's all the same monomer. It's got to be a double bond between these two carbons, and then the groups that are attached to those carbons would be on the end carbon, there's two H's, and then on the other end of the carbon would be a CH3 and an ester. So the key to thinking about this one is to identify the smallest repeating unit, and then make sure you don't flip any groups or interchange any groups when you're trying to decode what monomer it might have come from. This arrow, this big arrow, is what's called a retrosynthetic arrow. It's the first time we've seen this kind of nomenclature, I think. When you see the really big arrow pointing backwards, what this essentially says is, read this as could come from. So if you wanted to make this polymer, what starting material would you use in order to make it? What monomer could it derive from? And so we'll take this, we'll draw these two carbons, and I'm going to put a double bond between them because it's got to be an alkene. Alkene polymerization works by a radical process, and it's got to be a double bond. And then on the left carbon, I'm going to draw two H's. And then on the right carbon, I see there's a methyl group, and I see there's a carbonyl OCH3. I'm going to draw those features. This molecule is the monomer that polymethyl methacrylate comes from, and it is called, as you might imagine, methyl methacrylate. So that's an important type of radical polymerization polymer. It doesn't have a recycling symbol because it's not like a single-use plastic that people might use once and then either throw away or recycle. It tends to be in durable goods, like plexiglass windows tend to last for a long time. So durable goods are different than single-use packaging type materials because there isn't as much volume of plastic produced. So that's how you do this backwards thinking to figure out what monomer or monomers were used to make a polymer. And there's like one question like this in the homework. So, okay. Fantastic. Any questions about polymers or materials like that? Yeah.
I'm just curious, when plexiglass like yellows, does it change the structure of it at all?
It's a good question. Yeah. A lot of times, many polymers are sensitive to light. For example, PVC is one that's a really good material for pipes, but you can't have them be outside exposed because the light will degrade the plastic, make it brittle, and then it doesn't work very well anymore. So plexiglass yellowing, I don't know the specific mechanisms, but it's probably light that eventually causes reactions. So light, it carries energy, and it has the ability, if it's a short enough wavelength, high enough frequency, it can break a bond, and then you start to get changes in the plastic that can produce impurities that have color, like yellow or whatever. So yeah. Definitely light exposure is a way that polymers can degrade. All right, good question. Okay, let's talk about dienes some more. So we'll get back to the chapter content, and last time we discussed conformations of dienes that were called s-cis and s-trans. Let me just review what was meant by that. So if you have a diene, and I'm going to use a simple diene, a simple conjugated diene. This is 1,3-butadiene or 1,3 or but-1,3-diene. There are two conformations for this molecule that are conjugated. There's this one, and you can rotate about that central carbon-carbon bond to put it in this other conformation. The thing to look for to distinguish these is look at the single bond that's between the two double bonds, and imagine drawing like an imaginary line through that single bond. When the two alkene groups are on opposite sides, this is called s-trans. And the S stands for single bond. And when the two alkene groups are on the same side of the line, this is called s-cis. And the cis refers specifically to the single bond, the S. So when you see s-trans and s-cis, don't think alkene stereochemistry. It's not about a cis alkene or a trans alkene. It's about the single bond between two alkenes. And that's good to keep straight. Generally, the S-trans is more stable because there's less steric strain. The S-cis is a little less stable because there's more steric strain. I built a model of butadiene, and wanted to share it with people. I am not sure how well you're going to be able to see this, but the green lobes represent p orbitals. And so the molecule is conjugated when all of the p orbitals can overlap. So in other words, there's what we consider normally a double bond here by the overlapping p orbitals on the left side of the molecule, and a double bond here by the overlapping p orbitals on the right side of the molecule. But there's also double bond character between them when the p orbitals are lined up like this. Now, when you rotate the molecule, you're breaking the conjugation when you do that, because now the p orbitals aren't parallel to one another, they're perpendicular and they can't overlap. So this would be a non-conjugated conformation. It'd be a higher energy conformation. But if you rotate it around, you get to the s-trans. Now you've got that overlap again established. So the two conformations I have up on the board here, s-cis and s-trans, those are two conjugated conformations. And there's some barrier to rotation about that central bond because there's some double bond character through there, because there's some overlap between these overlapping p orbitals. All right, well, let's talk about what happens when you start putting groups on the ends of the diene, because there's some steric strain consequences that are important, and they're going to be important in understanding some aspects of the Diels-Alder reaction, which is where we're headed next. So let's talk about those. So we're going to look at a conjugated diene that's just a little bit more complicated than the one on the previous example. This one is going to have, do this. Okay. So there's a diene. It has a methyl group here and a methyl group here. Let's figure out where the single bond is that we worry about when we're talking about s-cis and s-trans. It's the one between the two alkenes. So I'm going to draw my line through there. And I'm going to say, okay, this is s-trans conformation. Everybody okay with s-trans? All right, now let's rotate this double bond over this way. So I'm going to take this molecule, rotate about the central carbon-carbon bond, and just flip it over. That's going to give me an s-cis conformation that looks like this. And since the two alkene parts are on the same side of that line that I drew, this is s-cis. Okay, as far as steric strain goes, there isn't a real big problem with steric strain in this molecule. There is an H here and there's an H here, and they do get in each other's space a little bit. And I built a model of this one to show you what that looks like. It is a steric strain interaction that makes s-cis less stable than s-trans, but not really dramatically so. So here is the molecule in the s-trans conformation. And then if I rotate this bond like this, now I'm in s-cis. And true, the two H's here, I'm going to artificially bend the molecule to make them touch. They're close to each other, but it isn't terrible. Okay, well, let's see what happens when we start messing with the positions of these bigger methyl groups. The issue, or the thing that's helping here, is that the two big methyl groups here and here are really far apart. They're not anywhere near each other, so that helps. But let's change that a little bit and look at another example. So what I indicated with this set of arrows is that the s-trans is more stable, s-cis is less stable, but they're not too far apart. Let's look at an example where they're starting to get further apart. One thing I should point out is that, and just remind you of, is that s-trans and s-cis is independent of the alkene geometry. So I just want to point out that this double bond right here This is an E double bond, like trans, entgegen, because the two large groups, high priority groups, are on opposite sides of a line that bisects the double bond. This is also an E alkene. I'll just put an E there just to remind you. But E and Z are separate from this s-cis, s-trans concept. And when you rotate the bond, you change s-cis and s-trans, but you don't change the nature of the alkene. If it was an E alkene over here, it's still an E alkene over here. So we're not rotating about the carbon-carbon double bond. We're rotating about the carbon-carbon bond between the two double bonds. So that's E, and this is still E. So rotating into different conformations does not change the geometry of the double bonds in this diene. That's a big take-home message. And it's easy to make a mistake when you're drawing two conformations where you accidentally flip an E or a Z relationship. So be careful not to do that. Okay, well, let's take a look at this example. This is a related example, and if we look at the single bond between the two double bonds, there's that line. This is, again, I'm sorry, I did the s-cis first. I want to do s-trans first, just to keep it consistent. So I'm going to do s-trans here. So here's an s-trans conformation of an alkene that has an E double bond up top and a Z double bond down here. So this has not too bad in terms of steric strain. It's not too bad. But let's take a look and see what happens when we reverse or rotate about that central carbon-carbon bond. Then we get to an s-cis conformation where, if you look at this line, it's s-cis because the two alkene parts are on the same side of that line. There's a lot more steric strain problem that's occurring because methyl is pretty big. Hydrogen might be small, but methyl is big. So there's some steric strain here. So I'm going to say this is increased steric strain in this particular conformation especially. So it's harder for this molecule to adopt s-cis conformation just because there's more strain associated with it. Let me build a model of this and show you how it looks. So this structure represents s-trans. So I've got my hands on the two bonds that are going to be rotating. Now I'm going to rotate this over into s-cis. So the problem with s-cis is that the methyl group is pretty big, and it gets pretty close to that hydrogen. So there's some serious steric strain that's developing, much worse than in the previous example, because this methyl group right here is pretty big and it's getting close to this hydrogen. So this is a less favored conformation than the s-trans by a larger amount than in the previous example. So, I'm going to make these arrows a little different. The arrow going back to s-trans is larger, and the arrow going to s-cis is smaller, indicating that equilibrium really favors s-trans by a larger amount. The molecule, put it another way, the molecule has a harder time adopting this s-cis conformation because of the increased steric strain. It doesn't spend as much time in this conformation. All right, let's look at another example where things get even worse. All right, in this example, both of the alkenes are going to be Z alkenes. So I have a Z alkene here, and I have a Z alkene here. That Z, remember, stands for zusammen, means that if you look at the two high priority groups about this alkene, they're on the same side of an imaginary line that bisects that double bond. Then let's look at the single bond between them. It's right here. So this is an S-trans version of the molecule. I'm going to be really dramatic with my arrows here and say that the s-cis version of this molecule, this conformation, is going to be really unfavored. It's really high in energy. Do that, and I'll say here s-cis. We'll label that as s-cis. So, it looks bad on paper, or on the board, I should say, because the two methyl groups are obviously close. And if you know that methyl is, a big group, then you know what we're talking about here. But let me show you the molecule in a model form, and then you'll really, I think, see it. All right, here we go. Here's the molecule in its S-trans conformation. I've got my hands here grabbing the molecule at the two ends of the single bond in the middle. And then if I rotate to put it into S-cis, you can see, the methyl groups are really just on top of each other, and that's a very bad steric interaction. So the molecule would have to bend, like distort its bond angles significantly in order to accommodate the space needed to get those methyls close together, and that generates some angle strain. So this is not a very good conformation. It has a really hard time adopting this conformation. So as far as like the examples go, what it's trying to do here with these three examples is illustrate that as steric strain in the S-cis increases, it gets less and less easy to adopt that conformation. There's less and less of it. And that'll be important later as we go along and talk about that. Okay, any questions about that? All right. Well, let's talk about stability of conjugated dienes. I've been saying, yeah, conjugation stabilizes things and not really providing any evidence until now. So here's some evidence. Because in chemistry, we always like to test things. We got to have like a hypothesis, and we got to do an experiment. We got to get a result, and the result's got to explain why we think we're right. So here's my thesis. Conjugation stabilizes dienes. And the way we know that this is true is hydrogenation experiments provide the proof or the evidence that you can interpret to support this. And let me just explain the experiments that are done, or were done. So you probably remember back when we were talking about reduction reactions, right after we got done talking about NMR spectroscopy, we talked about reductions, and the first reaction we talked about was hydrogenation of alkenes. And we said if you have an alkene like this, for example, and you put hydrogen in there and a catalyst like palladium on carbon, that the hydrogen can add across the double bond and you get out an alkane, but you also get some heat out because the product is overall has more stable bonds than the starting material because you exchange a weaker pi bond for a more stable sigma bond. So the difference then in the energy and in the stability comes out as heat. So there's a delta H value for this reaction that is 126 kilojoules per mole. So the delta H here is equal to minus 126 kilojoules per mole. It's negative because heat is coming out. here is another alkene. And if you put hydrogen and palladium on carbon in with this one, it adds across that double bond. And you get the same alkane in this case. And there's a delta H value. Now, flashback to that chapter. Would you expect more or less heat to come out of this reaction than that one? Less, because this one is more stable and this one is less stable. So if you've got a less stable alkene, it has further to drop down when it goes to the alkane. So more heat, less heat. So you get less heat out of this one, and the exact number is minus 113 kilojoules per mole. And by the way, the reason is substitution. This is a disubstituted alkene. That's a monosubstituted alkene, and more highly substituted alkenes are more stable. Excuse me. All right, well, these are some reference values. We're going to use these to try to understand energies and heats that are released when we start hydrogenating dienes. So we're going to go over to the next board and talk about an experiment that was then done based on the data that we just talked about. So here's a hydrogenation experiment. Imagine you took an alkene that looks like this, and you put it in with 2 equivalents of hydrogen and palladium on carbon. What do you think you'd get out of this in terms of heat? If you had to model it with the 2 energy values that we got over on the other side. Well, if you look, this is a monosubstituted alkene, and there's another identical monosubstituted alkene. So really, it's probably just going to be twice that minus 126 value that we got in the reference spot. So getting this alkane would produce, if we do delta H predicted, would equal 2 times minus 126 kilojoules per mole, which is equal to, let's see if it fits on the board here, minus 252. Minus 252. Kilojoules per mole. And the delta H experimental is equal to minus 252 kilojoules per mole. So that's exactly what we were expecting. So it makes us think that we understand this system pretty well. And I think we do. This is an isolated diene. Isolated diene, meaning the double bonds aren't close enough to be conjugated. It's non-conjugated. And there's nothing funny going on, no special kinds of energy results. But now let's take a look at a conjugated variant. If we do the same experiment with this diene, this one is conjugated. And let's see what happens. You put this in with 2 equivalents of H2 and palladium on carbon as your catalyst. You add hydrogen across each one of the alkene double bonds. You get an alkane there, and then there's delta H predicted which is going to be equal to the sum of the two alkenes that we used for reference on the previous board. Because one of them is a monosubstituted alkene, and one of them is a trans disubstituted alkene. So we have these two different energy values. This was minus 126, this was minus 113. So what you predict is minus 126 plus minus 113 kilojoules per mole, and that's equal to, let's see what we get for that, minus 239. Minus 239 kilojoules per mole. Okay, let's see what we actually got. Delta H experimental, what was actually measured was equal to minus 226 kilojoules per mole. So there's some energy missing here, some missing energy. And that's what is called resonance stabilization energy. So here's the difference. The resonance stabilization in this example is the difference between these two. So that's 13 kilojoules per mole. What this is saying is that because it's conjugated, the conjugated alkene is more stable than the non-conjugated one by this much. And whether you call it a negative or whether you call it a positive depends on whether you subtract this one from that one or this one from that one. But what I'll say over here is, I'll put this into words so it's clear. Conjugation makes this diene 13 kilojoules per mole more stable than you would otherwise predict. So it clearly makes a difference. Putting the double bonds together is having a stabilizing effect. So that's an important thing that we're going to look at a lot in the coming chapters too. This is our first introduction to it, but when we start getting later on, especially into the aromatic chapter, which is coming up, this is going to be a big deal. So do you have any questions about this so far? Okay, so putting molecules, arranging atoms in a way that provides conjugation stabilizes the molecule. Okay, well that preps us for this new topic that we're going to talk about, which is the Diels-Alder reaction. Diels-Alder reaction. So the Diels-Alder reaction was the subject of a Nobel Prize a while back. It's a reaction between two species, one called a diene and one called a dienophile. And the two chemists were Kurt Alder and Otto Diels. Otto Diels and Kurt Alder were the two chemists that came up with it. Otto Diels was the primary investigator, I guess, and Kurt Alder, I think, was his student. And so this is a reaction that is so powerful they decided to give the Nobel Prize for it because it does a lot of work. So there's two pieces. There's something called a diene, and it must be conjugated. And that's this piece. And then there's something called a dienophile, which is this piece. And it's some kind of double bond containing species. And what happens, and it means lover of dienes. And so when you put them together, what happens is they form a 6-membered ring transition state like this, where these dotted lines that I'm drawing indicate where there's going to be some new bonds forming. And then what happens is the electrons move in a way that forms those bonds. So the way we represent it, there's a way you can predict how this is going to happen, and it involves moving 3 pairs of electrons in a row. In reality, all the electrons move at once, but we're going to take our arrows and push them 1 pair at a time around in a circle. You can start with whichever pi bond you want, and you can push them either clockwise or counterclockwise, it doesn't matter. But if you want to start, say, for example, at the dienophile pi bond, you can do that and take a pair of electrons from there, out of the pi bond there, and show them going to make a new bond to that carbon of the diene. So we're going to make a new carbon-carbon bond here using the pi electrons in that alkene. Then if you make a new bond to that carbon, you have to lose a bond because carbon can only make 4. So you need to take the electrons out of this pi bond and push them that way. And then you're going to make a new pi bond here. And when you do that, this carbon then has to lose one of its bonds because it's getting a new bond. So this pair of electrons goes over here like this. So it's pushing the electrons around in a circle. Like I said, they all move at once. It's not like it happens in sequence like that, but this is the way we're going to predict what bonds form and what bonds break. And we're going to end up with the ring. The ring is going to look like this. It's going to be a cyclohexene. And just to specify what happened, the new bonds that we formed are right here. There's a new pi bond. That is a new sigma bond. And that is a new sigma bond. So let's keep track of the new bonds that we formed. We get 1 new pi bond. That's that bond right there. The pi bond of the double bond is new. And then we get 2 new sigma bonds. That bond is a sigma bond, and that bond is a sigma bond, and those bonds weren't there in the starting material. So those are our new bonds. These are releasing energy. So when you form these new bonds, you get energy out. Over here, let's keep track of what broke over here. We're breaking a pi bond here, a pi bond here, and a pi bond there. So we're breaking 3 pi bonds. So 3 pi bonds break. And the reason that matters is that now we can do a little bit of estimating as to how this reaction is going to shake out energetically. Pi bonds are weaker than sigma bonds. So if you break 3 weak bonds and then in the product you form back 1 of the weak bonds but 2 stronger sigma bonds, I'm just going to put that in here. This is energetically favorable in that the products have stronger bonds than the starting materials. Cyclohexene bonds in product are stronger than in starting materials. So the overall delta H for this reaction is going to be negative. Delta H is negative. It's an exothermic process and heat comes out. So when you do Diels-Alder reactions, you can expect there's going to be some heat produced. Let's continue this energy discussion over on the other board, but I want to ask you first, what do you think about entropy? So there's two components to overall energy. There's the enthalpy part, the heat part, and we said here delta H is negative. What do you think is going on with entropy? Are we decreasing or increasing disorder? Yeah, decreasing. We're putting some order into the system. We're taking a starting material which has two pieces, two parts, and then we're stitching them together into one. So we're reducing molecular motion. We're ordering the system. Delta S is going to be negative also. The change in entropy is going to be negative. We're decreasing entropy. So let's put this, I'm going to put this up on the board over here and we're going to talk about it. So for the Diels-Alder reaction, delta H is negative. Heat given off. Delta S is also negative because disorder decreases. So let's consider what that means in terms of the whole energy overall. So delta G is equal to delta H minus T times delta S. Do you remember that equation? Yeah, it's a good one. Classic, the big energy equation. Delta G is overall energy. Is the reaction going to go to products or favor reactants or products? That's what this means. If it's negative, products are favored. If it's positive, reactants are favored. This is what really matters. And there's two parts to it. There's the delta H part. And we just said delta H for this reaction is negative. That's going to tend to make delta G negative as well. So when delta H is negative, that tends to make delta G negative. Delta S is a little bit tricky because it's multiplied by a minus T term. So delta S in this reaction is negative. So you take a negative times a negative, you get a positive. So this term is going to be positive. That's going to tend to make delta G positive. So what I'm saying here is these two terms are in conflict. They disagree on whether the reaction should happen. Entropy doesn't want the reaction to happen. Enthalpy does. And when it matters, so temperature matters a lot because temperature influences the importance of the entropy term. So when temperature is low, like at room temperature, I'd say that's pretty low compared to temperatures that you can get that are thousands of degrees. So at room temperature, if this is low, the S term is less important and delta H dominates, and then the Diels-Alder reaction wants to happen. So generally, at room temperature, Diels-Alder reaction is favorable. As you heat it up, the Diels-Alder reaction becomes less favorable, and eventually at some temperature, it becomes reactant favored. So basically, this is how temperature can work to influence a reaction. So at high temperatures, it wants to stay at reactants. At lower temperatures, it wants to go to products. So some stuff about energy of Diels-Alder. Yes, there's a question.
Experimentally determine what temperature that is?
It depends on the specific delta H and delta S values for each molecule, but yeah, you could calculate it, and yeah, and if there are reactions, the reverse reaction of the Diels-Alder is called a retro Diels-Alder, so going in that direction. So if you want to do a retro Diels-Alder reaction, you'd want to do those at higher temperatures because that's where they're more favored. If you want your Diels-Alder reaction to work, do it at lower temperatures. So that's a little discussion of how that works. Let's take a look at all the stuff that happens in the Diels-Alder reaction. Before I erase this board, I want to just comment on some of the things that are going on here. There are a bunch of new bonds that are formed, a ring, and in a number of cases, depending on what your diene looks like and your dienophile looks like, you can have up to 4 stereogenic centers that are formed in this reaction. That atom, that atom, that atom, and that atom can all potentially be stereogenic centers. So the molecule, the reason this reaction won the Nobel Prize is very powerful. It makes a bunch of bonds, it makes a ring, and it potentially makes up to 4 stereogenic centers. So it builds a lot of complexity really quickly. And when you can do that in a controlled way, that's a really powerful process to have. And so that's why Diels-Alder reaction was considered such an important reaction in organic chemistry. Okay, well, let's talk about some of the features of Diels-Alder. Like, what are the things that influence when it works and how it works, when it's good and when it's not good? There is no perfect reaction. Diels-Alder is very good, but it doesn't always work well. And it's important to understand, in order to make use of its potential, when it might produce good results and when it won't. So these are some specific rules for Diels-Alder reactions. Rules for Diels-Alder reactions. First rules have to do with dienes that I'll talk about. Dienes must be conjugated. That's the first rule. Diels-Alder reactions doesn't work with dienes that are not conjugated. It has to be conjugated and able to adopt an s-cis conformation. So this is the reason we were going on and on about those dienes earlier, is that the ability of the diene to adopt an s-cis conformation directly impacts its ability to do Diels-Alder reactions. So let me show you a few dienes to illustrate this point. Here's a diene that works really well in Diels-Alder. It's one of the best. It goes really fast. Diels-Alder reactions with this diene are very good. And so it is in an s-cis conformation. Let me just get my orange chalk and show you. Both of the alkene parts are on one side of that line. And here's the thing. They're connected by this CH2 group in a way that prevents them from ever being S-trans. This molecule could not become S-trans if it wanted to, because it can't rotate about this bond because it's locked in place. So this molecule is locked in a reactive s-cis conformation. Locked in reactive s-cis conformation. So this is going to give a fast Diels-Alder reaction. Because of that, it's already organized into the conformation it needs to be in to react. Let's take a look at a different diene. This diene is is one that can exist in both s-cis and s-trans conformations. When it's in the s-cis conformation, it's reactive. When it's in s-trans, it's not reactive in Diels-Alder reactions. So it's kind of in the middle. It's not always perfectly positioned to do a Diels-Alder reaction, but it can organize itself into the position that it needs to be in. So it can react by Diels-Alder, but it's not as fast. So this is going to be a slower Diels-Alder reaction. And I'm just going to put a line here between these to make sure they don't like blur together. There's a molecule like this. This is an example of one that is kind of the opposite of the one that's on the left. This molecule is stuck in the unreactive s-trans conformation, locked in unreactive s-trans conformation. And this would give no Diels-Alder reaction, or no reaction in Diels-Alder. So in a sense, this one is the slowest of them all. So it doesn't work at all. So there's this hierarchy of reactivity. And then in this realm right here, you can think about all those permutations where we had methyl groups at the ends of the diene in various places. Those that had methyl groups positioned in spots that gave a lot of steric strain would react more slowly because they decrease the amount of time the diene is in s-cis. And if there's less steric strain, it's more reactive because it's in s-cis more of the time. So that's the first thing. It's the reactivity of the diene influences Diels-Alder. Any questions about that? All right, let's talk about the dienophile next. The Diels-Alder reaction fundamentally involves electrons flowing from one reactant to another. And the way it usually works is that the electrons usually flow from the diene into the dienophile. So it helps if the dienophile is electron poor and the diene is electron rich. So what people have found is that usually for dienes, dienophiles I should say, they are more reactive when they have electron withdrawing groups attached. Electron withdrawing groups attached. For example, C double bond O. C double bond O isn't the only example, but it's a real common one. So here's an example of how CO containing groups affects reactivity. So here is a dienophile. The dienophile part of it, this is the part that reacts, that forms the six-membered ring. But this carbonyl group influences the reactivity by withdrawing electron density out of that alkene. The way it does that is it can, by resonance, suck electron density up onto the oxygen. That makes this dienophile part of the molecule more electron poor, and it's easier for the electrons to flow from the diene into this, and that's why this is more reactive. So that's one example. All sorts of examples that contain groups with carbonyl. There's ester examples, there's carboxylic acid examples, aldehydes, ketones. I mean, there's just tons of them. Any C double bond O that you can think of, if it's directly attached to the carbon of the dienophile, is going to be an electron withdrawing group. You can have two, and that would make it even better. So like, for example, this molecule with a couple of different, just draw the carboxylic acid here, a couple of different carbonyl groups is even better. There are other withdrawing groups too. It isn't just carbonyl groups, those are the most common, but C triple bond N is another really common one because the C triple bond N can withdraw electron density from the dienophile. Another one that's really common is one called nitro, which we haven't talked about yet in much detail, but we'll get to this one in a little bit. So this group, the N with two O's and this Lewis structure is called a nitro group. And the nitro group is a very powerful electron withdrawing group because it can withdraw electron density from the dienophile part, the carbon-carbon double bond, by sucking electron density out of it up onto its oxygen. So these are all examples of groups that would make the dienophile part more electron poor and more reactive. So if you're trying to decide where's my diene and where's my dienophile, because that's the first thing you have to worry about, look for a couple of things. Look for a diene that's conjugated, because you need that, and then maybe circle that. Then make sure you can get it into the s-cis conformation, because you need to do that. Then the other part would be the dienophile. Make sure you can locate the carbon-carbon double bond in that molecule, and probably it's going to have an electron withdrawing group attached. A C double bond O, a carbonyl group of some sort, maybe a nitrile, maybe a nitro group. But then when you have those two, what we'll learn to do is to park them next to each other to make that transition state and then push the arrows. So that's what we'll work on when we come back next week. So have a good weekend. See you then.